So we're starting our next unit on rational functions. So we have been through several of our parent graphs, obviously linear functions, quadratic functions, third degree polynomial functions, fourth degree. We've done exponential functions and logarithmic functions. We have touched upon functions with radicals and absolute value. So now we are looking at our rational function. So what makes a rational function? All right, what makes a rational function? Well, first of all, a rational function is typically going to be a polynomial over a polynomial. And I would encourage you to also use the key that is attached in this post. And so if you write out polynomials, basically we are saying that we don't have negative exponents, we have coefficients, we don't have radicals, we have exponents that are whole numbers. All right, so one of the reasons, the main reason we do this unit is because the rational functions have asymptotes, horizontal and vertical asymptotes. And asymptotes help us develop the idea of limits, which is a foundation for calculus. Okay, so the first question asks, are these polynomials or not? Because if a function is not a polynomial function, or a rational function rather, excuse me, if it's not a rational function, the patterns that we see with asymptotes do not apply. Okay, so example 1, this is a polynomial, but this is not because of the radicals, so no. Example 1b, this is a polynomial, this is a polynomial, so yes, that's a rational function. Polynomial over polynomial. So again, we have to, first of all, identify whether it is a rational function, because if it isn't, the patterns we use to find vertical and horizontal asymptotes do not apply. Okay, so let's take a look here, and it is asking us to determine whether this is a function, a rational function, and then name the domain. All right, so taking a look at example 2a. Well, if I need a polynomial over a polynomial, this doesn't look like that. So I'm going to have to get a common denominator. So my common denominator is x plus 1 over x plus 1. And then distribute and put our like terms together. And so we have 4x plus 5 over x plus 1. So we know that my domain will be all reals except -1. So negative infinity to -1 and union with -1 to infinity. Purpose of that question, a couple of reasons. One, it gets us to be thinking about rewriting when something is in this form to put it as a rational function, but also gets us thinking about that we know we're going to end up with a vertical asymptote at -1. Okay, part B is definitely cleaning up a complex fraction, and we reviewed complex fractions in our first unit, but we need to know how to simplify this. So first of all, I would not deal with the 1 at first. I would clean up or clear this complex fraction, so I would multiply the numerator and denominator by the LCD of x, distribute my x, and then once I distribute my x, I end up with 1 plus 2x over x squared plus 3. Again, a rational function is a polynomial over a polynomial, so we need to get a common denominator. And so we would have x squared plus 3, over x squared plus 3 plus 2x over x squared plus 3. So our rational function is x squared plus 2x plus 3 over x squared plus 3. Now, if we look at the domain, no matter what I put in for x, I'm going to get a positive or 0. So there aren't any values by this domain that it looks like I have any issues with. However, we also should always look at our original function. And we know by our original function here that x can't be 0. So we look at our final simplified version, but we should also look at the original function. So my domain is all reals except 0. All right, so now that we know what a rational function is, we know that most rational functions have asymptotes in them. So what is going to give us a vertical asymptote? Okay, we've already talked about this, but let's be clear that it is where we have undefined values. All right, so when we have a vertical asymptote, that means x is undefined. So where does that happen? Well, of course, we cannot have our denominator equal to 0, or we cannot have negative under the radical. All right, so now that we've talked about rational functions, every time we've worked with functions, we've talked about their parent graphs. So going back to Unit 1, some basics on parent graphs, and even Unit 3 when we talked about transformations, let's go to our parent graph of y equals 1 over x. Technically, this is a special case of a hyperbola, but once I start adding and subtracting numbers, it no longer is a hyperbola. Okay, so first of all, we know that this is undefined at 0, so we know we will have a vertical asymptote at the y-axis, or x equals 0. So x equals 0 is our vertical asymptote. And remember, a graph will never intersect or cross a vertical asymptote because it is undefined there. So how do we describe behavior? Well, we describe behavior of rational functions around their vertical asymptotes. And this is why with logarithmic functions, we talked about left and right side. So if I said as x approaches 0 from the right side, that's how I denote that. We know y goes to infinity. And as x approaches 0 from the left side, y goes to negative infinity. Now, rational functions are a broad category. Once we start adding and subtracting numbers, we know this is going to be transformed. But once I start throwing in quadratics and third degrees, this is actually going to change the look of the graph. So the point of this is we have to know what to expect. So when I'm graphing these, I should always look for my asymptotes first and sketch that, because what's going to happen in our calculators, just like with the logarithmic and exponential functions, sometimes the calculator graph's a little misleading, and that's why we have to know what to expect. Sometimes parts of the graph aren't even showing, and sometimes it looks like the graph stops at the asymptote, which we know it does not. So let's take a look at the next example. I am asking you to tell me the vertical asymptote, and I'm asking you to graph it and describe behavior. Well, first of all, let's go back to this and let's not forget about transformations. If this is the parent graph, multiplying by 2, we know it's going to vertically stretch it, and this is going to translate at left 1. So if this is translating at left 1, we know we have a vertical asymptote at x equals negative 1. We also know that because that's where it would be undefined. All right, now vertical stretch, I just actually picked some numbers here. I put in 0 and I would get 2. I put in 1 and I would get 1 just to show the graph. So how would I describe beginning and ending behavior? I would say that as x approaches negative 1 from the right side, it's going to infinity. And as x approaches negative 1 from the left side, it's going to negative infinity. Okay, now let's take a look here. Take a look at B. So first of all, I know I have a rational function, a polynomial over a polynomial, but once I start throwing quadratics in here, we can expect that we're going to be transforming what the graph even looks like from the parent graph. Okay, so first of all, I always encourage you to find your asymptotes first before you put these on your calculator. Again, the calculator sometimes doesn't give us the true image. We have to know what to expect. So I'm going to look at my denominator. I'm trying to find where it's undefined. Thankfully, it factors. And so it is undefined at 3/2 and negative 1. So those would be my vertical asymptotes. We always write those as equations. We don't write vertical asymptote equals. It is a vertical line, so we write it as an equation of a vertical line. Now, what I would encourage you to do is I would encourage you to go ahead and sketch your x and y axis and put in your vertical asymptotes. Then put it into your calculator. Because sometimes what's going to happen here is this part that I'm showing you, so if you need to stop the video and enter this, do that, but this part that I'm showing you may not show up. But ladies and gentlemen, if you know you have two asymptotes here, an asymptote is breaking this graph apart. So if I have two vertical asymptotes, that means I definitely have 3 curves in this graph. So that is also a predictor. All right, so let's describe behavior around the asymptote. So as x approaches negative 1 from the left side, y goes to infinity. As x approaches negative 1 from the right side, y goes to negative infinity. As x approaches 3/2 from the left side, y goes to negative infinity. And as x approaches 3/2 from the right side, y goes to positive infinity. Always know what to expect. Don't put it on your calculator first. Find your asymptotes. So speaking of asymptotes, now vertical asymptotes we've always talked about. Now let's get specific about horizontal asymptotes. Horizontal asymptotes are boundaries. The graphs are not undefined at horizontal asymptotes. They are boundaries. I compare horizontal asymptotes kind of like rivers on a bank. Sometimes the river follows along the bank, but sometimes if the water is high, the river goes above the bank. So a horizontal asymptote is a boundary that the graph may or may not cross, but it does follow along. Now, For right now, I'm just going to tell you how to find the horizontal asymptotes. Later on in the year, I will prove to you why horizontal asymptotes are like limits, and we'll see the pattern as to why this works. So here's the how you find the horizontal asymptote. You have polynomials, so you compare the degrees of the numerator and denominator. In other words, you take the highest exponent of each one and compare. Now, why? Well, I always look at it this way. Your leading term with the highest exponent has a lot of power. It determines what type of graph it is. So that's why we're looking at this. So if we compare the degree, so if my numerator exponent is less than my denominator exponent, my horizontal asymptote will automatically be 0. So if you take a look at our parent graph y equals x, we know our horizontal asymptote was the x-axis. Take a look at this one up here. If I compare the degree is 2x to the 0. 0 is less than 2, so the horizontal asymptote was the x-axis, or y equals 0. Now, if we compare and the degrees are the same, you got to think about this. If the degrees are the same, they about have the same power, if you will, and so you take their coefficient. And so my horizontal asymptote would be their leading coefficients, a over b. Now, we're not going to address this today, but when the degree of the numerator is bigger than the degree of the denominator, we can end up actually with non-horizontal or vertical linear equations, or even parabolas as asymptotes, and we'll talk about that on another day. So let's take a look at example 5. So find the horizontal asymptote. And so I compare, I have a rational function, compare my degrees, and the degrees are the same, so my horizontal asymptote is y equals 3/5. Now, I would encourage you to stop and go ahead and graph this, but you will see that no matter what, as x goes to infinity or as x goes to negative infinity, the graph is going to follow along the horizontal asymptote. So that's why I could say as x goes to infinity, y goes to 3/5, and I could say as x goes to negative infinity, y goes to 3/5. However, it's going to follow along both directions and go to 3/5. So that's why we say as the absolute value of x goes to infinity, y goes to 3/5. Okay, and part B, the degree of the numerator is less than the degree of the denominator, so I know my horizontal axis will be the x-axis, horizontal asymptote, or y equals 0. So I could say as the absolute value of x goes to infinity, y goes to 0. And you can see, for example, in this one, we know that this is a horizontal axis, and we know that as x goes on in both directions, that the graph heads to 0. Okay, I want to add one here, so please add this to the notes. If I have the function f of x equals 6 minus 1 over x, okay, so first of all, 6 minus 1 over x, that's not a rational function the way it is. So in order to compare degrees, I have to have a polynomial over a polynomial. So I should get a common denominator of 6x over x. So my horizontal asymptote would be, the degrees are the same, so it would be 6 over 1. So my horizontal asymptote is y equals 6. So describing this, I would say as the absolute value of x goes to infinity, the graph will travel along y equal to 6. Okay, so now let's put all of this together. So again, when you are asked to graph a rational function, do not put it on your calculator first. Figure out your vertical asymptotes, your horizontal asymptotes, and I would even go ahead and find a y-intercept, because that's easy. And then graph those, and you have an idea of how to interpret what's on your calculator. Okay, so let's take a look at example 6a. So 6a is a rational function, and it is undefined at x equals -2. So I would go ahead and make my list. So my vertical asymptote is x equals -2. All right, now horizontal, I'm going to compare the degrees. The degrees are the same, and so I'm going to take my coefficient, and so I have y equals 3. I'm going to find a point, so I have my y-intercept. If I put in 0 for x, I get -1/2. So when I graphed this, I should have probably waited to do this, but I graphed my vertical asymptote, my horizontal asymptote, I graphed my y-intercept, then I put it on my calculator. Now, something else, some vocabulary. This is considered a discontinuous function, or it has discontinuity because there's a break in the graph. Okay, and let's take a look here at B. So I have a rational function over rational function, so I'm going to find my vertical asymptote. It's undefined at x equals 3. My horizontal, the degrees are the same, so I take the coefficient y equals 2, and my y-intercept, if I put in 0 for x, I get -4/3. So before I put this on my calculator, I am going to graph my horizontal asymptote, my vertical asymptote, and my intercept. All right, last one. So I go to find my vertical asymptotes, but no matter what I put in, I'm not going to get anything that's undefined. So I don't have a vertical asymptote. I do have a horizontal asymptote. The degrees are the same, so my coefficient's 1 over 1, so it's y equals 1. I do have a y-intercept. If I put 0 in for x, y-intercept is 0, 2. So now if you put that on your calculator, so again, at any time, if you need to put something on your calculator, stop the video and do that. So I graphed my y-intercept at 0, 2. I graphed my horizontal asymptote. And once you see the graph, you can see that this does travel along the horizontal asymptote as I described that the graphs do. However, this is continuous because there is no vertical asymptote. There is no break in the graph. So with rational functions, find your vertical asymptotes first, your horizontal asymptotes first, find a y-intercept, and graph those first, then put it on your calculator.